Okay, in this video we're going to cover Atterberg limits. And the Atterberg limits were originally developed by an agricultural engineer who was studying the properties of soil and how sticky it would be and things like that for growing crops. But we've adopted it for soil classification. And the key concept here is that soil exhibits clayey soils exhibit a property called plasticity. And what that means is that it's just moldable, right? If you get a piece of modeling clay, you can work it into a shape and it maintains that shape. It holds itself together. Whereas if you took a handful of loose sand particles that were dry and tried to shape them, they wouldn't really retain their shape, right? You would make a shape and it would just fall apart and go back to being powder. So that ability of clay to hold itself together is what we call plasticity. I'm sure that you've experienced plasticity before. You know, all of us have played with clay at some point in our lives, and we know that it holds itself together, but you may not have given much thought to what actually is happening there. Why is it that clay minerals hold themselves together, whereas sand particles fall apart? They are, after all, just little particles, right? You can't maybe see the individual particles in a clay mineral, whereas you can see them in sand. And it turns out what's happening is that there are electrochemical interactions between the clay minerals. So what I'm showing here is the shape of a silt particle right there, or a sand particle. They're pretty bulky particles in that their surface area is generally not very big relative to their volume. Whereas here we have a clay mineral, right? It's like a flat plate. You can think of it as being shaped like a piece of paper rather than like a sphere, right? Sand and silt is close to a sphere. Clay minerals are close to a sheet of paper. And there's a charge on the surface of these particles. There's a charge on the surface of a silt particle, or charges on the surface of clay minerals. For a silt particle or sand particle, those electrical charges don't really influence the behavior of the particle itself because the mass is so big relative to the surface area. So if you kind of integrated all that charge, all that potential over the surface of the particle, it'd be very small compared with the mass. Whereas for a clay mineral, it's pretty big, right? So the clay minerals have these very strong electrochemical interactions that kind of dictate their behavior, and that's what makes them moldable. So the surface, the flat surface of a clay mineral, you know, on the bottom there and the top, tend to have a negative charge. That's just because of the crystal structure of the clay mineral. And then the ends have a positive charge. So what often happens is those positively charged ends will connect up with the negatively charged surfaces, and that gives it a little bit of cohesion. You know, it's an extra force holding those two minerals together, and that force is fairly big relative to the mass of the particle. All right, now in order to quantify this behavior, to classify soil, like how do we know if something is a silt or a clay? Well, one way to do it would be to look at the clay, look at the minerals, see if they're kind of bulky or if they're flat plates. You'd have to use like a scanning electron microscope in order to see most clay minerals because they're so small. And that's pretty expensive, specialized equipment, and it's not really feasible to do that for typical geotechnical projects. It's more in the realm of research. And there are some scanning electron microscope images of clay minerals that I can show you. They're pretty interesting, but we're not going to do that for typical projects. We could try and do a grain size test. Clay minerals are smaller than silt particles. So I mentioned that there is the hydrometer. That assumes that the particles are spheres and that they settle through viscous fluid according to Stokes' law. So silt particles do follow Stokes' law reasonably well. They're not perfectly spherical, but they're close enough. Clay minerals really don't, right? They might stay in suspension for a lot longer than we would predict based on one of their dimensions, right? The diameter or the thickness. It's just so far from being spherical that Stokes' law doesn't really apply. So it's hard to do it based on grain size. So what we do instead is base it on directly measuring plasticity. So how much water do you need to add to the soil until it reaches certain consistencies? You know, like the consistency of peanut butter would be like on the verge between being a solid and being a liquid. And then there's another limit that's like where it's starting to crumble and becomes really brittle. So Atterberg quantified these limits, and those things are easy for us to measure. All we have to do is get the soil to a specific water content that matches certain predefined physical characteristics, and then measure that water content, and those are the Atterberg limits. So we're going to talk about a couple of limits here. Just keep in mind these are all water contents. Okay, so the first limit we'll talk about is the liquid limit. And the liquid limit is the water content at which the soil transitions from behaving like a plastic solid that you could mold and sculpt with into basically like a liquid. It would be too runny, too mushy to really work with it at that point. Then there's the plastic limit, PL. And liquid and plastic limit are the two that we use to classify soil. So plastic limit is the water content at which a soil transitions from a semi-solid to a plastic solid. So semi-solid means that it's not like a dried up, desiccated little piece of clay. It still is workable, like you could sculpt with it, but it's becoming pretty hard, and you might have to put a lot of energy into moving it, and then it might be brittle and kind of crumble apart rather than sculpting, whereas a plastic solid is really deformable and moldable. Okay, and then there's another limit, the shrinkage limit, which is the transition from a brittle solid to a semi-solid. So it's even drier than the plastic limit. We don't use the shrinkage limit to classify soil, so we won't talk about it further here. So here's a little chart that shows the water content and the soil state. So the water content from 0 up to the shrinkage limit, you would call that a brittle solid. From the shrinkage limit to the plastic limit is a semi-solid. And then the range of clay water contents that we tend to worry about for geotechnical engineering applications lie somewhere between the plastic limit and the liquid limit, or maybe even higher than the liquid limit sometimes for really soft clays. So a plastic solid is between the plastic limit and the liquid limit, and then the soil is not really a liquid, but it's going to be very soft and weak in the range above the liquid limit. And then there's another limit that we define called the Liquidity Index, LI. And it's equal to 0 if the soil is at the plastic limit, and it's equal to 1 if the soil is at the liquid limit. So that's a convenient index for us to calculate, and it's defined here by this equation. The liquidity index is the water content minus the plastic limit divided by the liquid limit divided by or minus the plastic limit. And we only define it if it's between 0 and 1. If it's drier, we usually won't even quantify a liquidity index. All right, another important index is the plasticity index. So we've defined liquid and plastic limit. Well, it turns out that a really fundamental parameter that's closely related to the types of clay minerals that are in a soil is the difference between the liquid and plastic limit. If you have really flat, thin clay minerals, the liquid limit is going to be very high, and the plastic limit will be a little bit higher than other clays, but the difference between those two will be very big. If you have a clay that is, kind of not so thin, a little bulkier to where the mass of the particles have more of an impact than those surface charges, then the difference between liquid and plastic limit will be smaller. So we tend to use plasticity index to classify soil. And it's just equal to the liquid limit minus the plastic limit. Very simple calculation to do. A common mistake students often make is that they forget to take this difference, and they get confused between plastic limit and plasticity index. So always be careful about the notation. You should understand whether you're being asked to use a plasticity index or a plastic limit. They have kind of similar names, so it's easy to get them confused. Okay, so let's talk about the procedure for measuring these things. There's two different procedures that we use, and I'm going to transition now to a slideshow because the slideshow shows some of the equipment. So for measuring the liquid limit, we tend to use a device called the Casagrande cup. At least in the United States practice, the Casagrande cup is the most common way for us to measure liquid limit. And the way that it works is that we have a little brass dish here, and it has a cross section that looks like this, and then we fill it up with soil, So there's the clay that we put inside the Casagrande cup. First we sieve the soil and only use the fraction of the soil that passes through the number 40 sieve. So there's actually a little bit of sand typically in the soil when we do the Atterberg Limits test. It's not done just on the fines. Okay, so we put the little pat of soil in here, and then there's this grooving tool that we have that's usually made of plastic or brass, and we drag it through the soil and cut a groove, a V-shaped notch in the soil like that. You can see that notch right there, and you can see the shiny brass at the bottom of the notch, right? So it takes a little practice to get this right, but you want to make the soil kind of like the exact thickness of that space underneath the notching tool. All right, and then there's a handle on this thing, and the brass cup is on this sort of eccentric cam. So every time you rotate the handle, it raises the brass cup up a little bit, and then it lets it free fall, and it hits this hard rubber pad down below. And so what we do is turn this handle at a specified rate. I think it's about once per second is the required rate. And we watch this notch here, right? What will happen is every time you tap, the soil kind of closes in a little bit on that notch. And eventually it will close in over a distance of more than about 10 millimeters or 1 centimeter. So you can see the back end of the grooving tool has a 1 centimeter wide measurement tool, and you can hold it up there and say, okay, the notch has closed. I can no longer see the shiny part. It only has to close on the bottom. It doesn't have to collapse all the way in and touch on the top. As soon as you can't see the brass anymore over a 1 centimeter or 10 millimeter length, then you're done. And you count the number of taps that it's taken to get there. Okay, and then you repeat that. So you prepare the soil to a certain water content. You do the liquid limit test, and maybe it takes, say, 40 taps to close that groove. Well, then you add a little bit of water, mix the soil up again. You do it again, and maybe it takes 28 taps to close that groove. As you add water, it's going to make the soil close in fewer number of taps, right? Then what you would do is plot that out here. So here's the water content. Every time you make a measurement with the Casagrande cup, you measure the water content. So here's one at a low water content. It took 34 or 33 taps to close the groove. Then they added a little bit of water, and the water content goes up and the number of taps goes down. Then they get another one. They have 4 points here, and then they fit a line through those points in log space, right? So number of taps is on a log scale and water content's on a regular arithmetic scale, so semi-log plot. And then you come in at 25 taps, come up here and interpolate the water content at that point. And that's the liquid limit, right? So in this case, the liquid limit is what, 22.2%. So ideally, you could get all of your points right near 25. If you're an experienced technician, you can get that, and that's better. It may reduce interpolation errors a little bit if you can cluster your points around 25. You don't want to have points that are way out here at like 200 and then other ones that are way down here at like 3. You want to try and get them reasonably close to 25 so that you can interpolate accurately. Okay, so that's the liquid limit test. In other parts of the world, there's a separate test that's done. Instead of the Casagrande cup, they use what's called the fall cone. And you have a soil sample that's prepared in a brass cylinder, and then this cone is allowed to drop into the clay, and you measure how far it pushes down. And the cone weighs 80 grams and has a 30-degree angle on the tip. And then you position it so that it just touches the top of the sample, and then you release it for 5 seconds to see how far it pushes in. And the liquid limit is defined as the water content of the soil, which allows the cone to push in exactly 20 millimeters during that period of time in 5 seconds. So it's often difficult to obtain a test with exactly 20 millimeters. So you have to do the iterations again on the water content to get it to just the right consistency. There is a little bit of bias between the fall cone and the Casagrande cup. You don't get the exact same liquid limit using these procedures. So just be aware of that. There are corrections in the literature that can be applied, but most of the time you're going to be dealing with liquid limits measured with the Casagrande cup. Okay, then there's another test called the plastic limit test, and that's what's shown here in this figure on the bottom. And the way that the plastic limit test works is that after you're done with the liquid limit test, you take that soil that you've tested and you start working it with your hands, roll it out on a glass plate, start drying it out, and you want to get it to the point where you can roll a thread that's an 1/8 of an inch thick, or 13 millimeters thick. Sorry, not 13 millimeters, an 1/8 of an inch. The 13 millimeters is the groove's length in this case. So you want to roll it out to where it's an 1/8 of an inch thick, and you can't roll it to a thinner thread without it crumbling apart. So if it's too wet, you'll be able to roll it very thin and it will hold itself together. All that water is in there, making it pliable and easy to work with. So you have to keep drying it out, rolling it with your hand. You have to use like the really flat part of your palm right there, because other parts of your hand have little bumps that might cause it to crumble too early. And your goal should really be to see if you challenge yourself to see if you can roll it thinner than that 1/8 inch thread. And once you get it to crumble at 1/8 of an inch thickness and you just can't roll it any thinner, you gather up all those little pieces of soil and you measure that water content. And that's the plastic limit. So that's how Atterberg said to measure liquid and plastic limits. And that's still how we do it today. All right, and here's an indication of kind of the soil behavior. This is a chart that I already showed kind of in my notes, and it's repeated here, along with an indication of kind of the material response in terms of stress-strain behavior. So if you're in this zone of the plastic solid, the stress-strain behavior will be pretty weak and soft if the water content's equal to the liquid limit. Again, it's not zero, so the soil is not really a liquid. It still has solid properties, but it's very weak and soft. Once you get out to the plastic limit, it's going to be stiffer, so the initial slope will be higher. It'll reach a higher strength, and then maybe it will have some strain softening. So you get over that peak, and then it gets weaker. Once you get out here, beyond the liquid limit, it's very weak, and it could even become basically like a fluid kind of at that point. All right, now the way that we organize our Casagrande test results, or our plasticity Atterberg limit test results, is to put them on the Casagrande plasticity chart. And this chart tells you whether you have silt or clay. And it was formulated by Arthur Casagrande in 1948. And what you have here is liquid limit on the x-axis and plasticity index on the y-axis. So this is not plastic limit, this is plasticity index here on the y-axis. And so after you measure the liquid limit and the plastic limit, you can calculate the plasticity index, and then you can come and put a point on the chart wherever your soil happens to be. And there are a couple of important boundaries that we use in classifying soil. One is a liquid limit of 50%. So if the liquid limit's higher than 50%, we call it a high plasticity silt. So the H means high plasticity, or a high plasticity clay, right? So there's the B line. That's the first line that we'll talk about. If the soil has a liquid limit lower than 50, then it's a lean silt or lean clay, CL or ML. So the L stands for lean. Sometimes MH soils, high plasticity silts, are called elastic silts. I'm not sure why we have this correlation. Sometimes these are also called fat clays and lean clays. So anyway, just remember the H and the L, high plasticity, low plasticity. Easy to think about that. Okay, and then there are a couple of other lines. There's the A line, which is an important one for us, because that's the dividing line between clay and silt. So if your soil plots above this A line, it's a clay. If it plots below the A line, then it's a silt, ML or MH. And then there's this U line. We actually don't use the U line in classification. It just is kind of a boundary where you're not going to see soil above the U line. So clays tend to lie in this region here, bounded by the A line and the U line. Then there is one other little region of interest down here. The hatched region right there lies between a plasticity index of 4 and 7, and it's within what would be the CL region. So if your soil plots in that region, then we give it a silt clay kind of designation, CLML. two symbols. So it really is having properties of silt and clay both together. So it's like a silty clay or clayey silt, something like that. So anyway, that's how the plasticity chart works. The best way for you to present your Atterberg limits results is to put a point on this chart. So there are equations for these lines. It's easy for you to reproduce them, draw lines using Excel or something like that. Plot your point on the line and print that chart and put it in your report. That will show your client, exactly where your point lies, just like where I left the little red data point there, the laser pointer. It's a good way to do that result. All right, the last slide that I'll show for Atterberg limits is an aspect of clay behavior that's related to the flat plate-like nature of clay minerals, and it's sensitive clay. And there was recently a landslide in Norway that you may have seen in the news that happened in sensitive clay. And so what this slide is showing is a little cylinder of soil, looks like a triaxial test specimen or something, and it has a certain water content, and it's supporting all of these masses, right? 5 kilos, 2 kilos. This is a lot of weight. So this little soil cylinder is pretty strong. This soil in the beaker is the same exact soil as this soil, and it's at the same water content. Believe it or not, these two soils have the same water content. This one has just been remolded. So if you were to take this little cylinder of soil and start to deform it and move it around, it would turn into a liquid. So it's a pretty frightening behavior of soil, and you can see why that would cause landslides, right? If you come in and there's this stiff soil that you can build on, then it gets disturbed somehow and turns into a liquid. You can get these really big flow slides. And what's happening here is that the electrochemical interactions of the clay are highly influenced by cations in the water. So if a clay is deposited in the ocean as a marine clay deposit, the sodium from the seawater will be attracted to the negative surface of the clay mineral, and that will that will allow the clay minerals to come closer together. So it turns out water also has a slight positive charge, so you get water adhering to these minerals. And the water is not very strongly positive, so the clay minerals stay far apart from each other, and the positive end of the clay mineral doesn't come and click onto the negative surface of the clay mineral because the water is keeping them far apart. As soon as you get the sodium cations in there from the seawater, the sodium cations are much more highly positive, and the minerals come closer together because the negative charges aren't repelling each other as much, and then the positive end of the clay mineral will click into place. And so you get what's called a flocculated structure. That's where the clay minerals all kind of click together like magnets and form a structure that's like a house of cards. That structure, believe it or not, is pretty stable as long as the sodium cations stay in there so that the clay minerals are not repelling each other with those negative surfaces being so close together. But what happens is that marine sediments are often subsequently lifted up out of the ocean, like at the end of the Ice Age or something like that, and the sodium cations then come in contact with fresh water, and osmotic pressure pulls them out. So the sodium cations get leached out of the clay, and then they're still stable in that configuration, but as soon as you start disturbing them and that positive end of the clay mineral clicks off of the negative end, now they're pushing each other apart really hard, and it becomes like a liquid. So it's an interesting aspect of soil behavior. Fortunately, we don't have much sensitive clay here in Southern California. There is some of it in the northeast parts of Quebec in North America, and certainly through Sweden, Norway, and countries up there, but not so much of it here.